In the quietest depths of space, where galaxies are expected to gather and light should softly accumulate, modern instruments have found something unexpected. Vast regions where almost nothing resides, ancient light arriving without companions, structures appearing alone, suspended in darkness, separated by distances so large they strain intuition. With the help of space telescopes designed to see farther than ever before, astronomers have spent decades tracing faint signals from the edge of visibility. Data gathered by observatories orbiting Earth and drifting far beyond it have slowly revealed a universe that feels less crowded, less centered, and far more uncertain than once imagined. Measurements of distant galaxies suggest that space itself is stretching, not gently, but persistently. The farther away something lies, the faster it appears to recede. Beyond a certain distance, light no longer arrives at all. Not because nothing exists there, but because the universe has carried it beyond reach. What appears, from one perspective, to be an edge may instead be a limit. A horizon shaped not by walls or boundaries, but by time, expansion, and the finite speed at which information travels. A quiet boundary where observation ends, even if reality does not. Institutions like NASA and international space agencies continue to push that boundary outward, using instruments such as the James Webb Space Telescope to peer deeper into cosmic history. Each new observation refines the picture, while also revealing how much remains unseen. Tonight's journey explores that subtle boundary, not a cliff at the end of space, but a fading line between what can be known and what lies beyond observation. A place where certainty gives way to careful inference, and where mystery arises not from speculation, but from the limits of measurement itself. If the edge of the universe exists at all, it may not be a place, it may be a moment, a distance, or simply the farthest whisper of light still able to reach this quiet corner of space. Welcome to the Sleepy Scientist. If you enjoy drifting through questions like this, I invite you to subscribe and join these quiet explorations. And if you feel like it, share where in the world you're listening from tonight. It's always comforting to know how far these thoughts travel. Settle in. Let the universe stretch outward, slowly. When scientists use the word universe, they're usually pointing to something very specific, even if the word itself sounds wonderfully broad. In everyday language, the universe often means everything that exists. All space, all time, all matter, all energy, and whatever laws quietly govern how those things behave. In cosmology, the meaning is similar, but it carries a careful precision shaped by observation, measurement, and restraint. The universe, in scientific terms, is the total physical system described by space and time together. It includes galaxies and stars, dust and radiation, gravity and expansion. It also includes regions that have never been seen, and may never be seen. This distinction matters because science is built not just on what exists, but on what can be tested, measured, and compared against evidence. This is where another phrase enters the conversation, one that sounds similar but behaves very differently. The observable universe. This is not a different universe. It is not a special region carved out by nature. It is simply the portion of the universe from which light has had enough time to reach this location since the universe became transparent to radiation. In other words, it is the part of the universe that can be observed in principle, given the finite age of the cosmos and the finite speed at which light travels. That distinction can feel subtle at first, but it changes how questions are asked. When scientists describe the size of the observable universe, they're not describing the size of everything. They're describing a horizon, a boundary defined by time and motion, not by walls or edges. Beyond that horizon, the universe may continue smoothly, following the same physical laws, filled with galaxies much like the ones already seen. Or it may differ in ways that cannot yet be tested. Science remains careful about drawing conclusions where evidence cannot reach. Language becomes especially important at these scales because intuition struggles. Human experience evolved to navigate landscapes, not cosmic distances. Words like edge, boundary, and outside come loaded with everyday meaning. In daily life, an edge usually marks a sudden stop. A wall implies separation. An outside suggests a surrounding space. In cosmology, those assumptions often fail quietly but completely. When scientists say the universe has no center, for example, they do not mean that no point can be chosen as a reference. They mean that the expansion of space looks the same in every direction, from every large-scale location. There is no special middle where everything began spreading outward. Every region sees other regions moving away, not because they are fleeing a central point, but because the space between them is stretching. Similarly, when the universe is described as expanding, it is not expanding into anything. There is no surrounding emptiness waiting to be filled. Expansion is a change in distance relationships within space itself. This is one of the reasons the phrase observable universe is so useful. It acknowledges that what can be seen depends on how space and time behave together, not on the existence of a cosmic container. Scientific language evolves alongside technology. Definitions sharpen as instruments improve. What once counted as the edge of observation has shifted many times over the past century. Early telescopes revealed nearby galaxies. Later ones uncovered vast clusters and filaments. Space-based observatories removed atmospheric interference, allowing faint and ancient light to be detected with greater clarity. Each improvement extended the reach of observation, without changing the underlying distinction between what exists and what can be seen. NASA and the European Space Agency play an important role in this process, not by declaring what the universe is, but by providing the tools and frameworks that allow consistent measurement. When a space telescope surveys distant galaxies or maps background radiation, it does more than collect images. It refines definitions. It tightens uncertainty. It helps scientists agree on what is being described when words like universe, observable region, horizon, and distance are used. Standardization may sound dull, but it is essential when discussing something this vast. Without shared definitions, comparisons break down. One group's universe could mean another group's observable volume. One measurement of size could refer to distance now, another to distance at the time light was emitted. Clear language keeps the conversation grounded, even when the subject matter stretches far beyond ordinary experience. There is also a quiet humility built into these definitions. The observable universe is not presented as a complete picture, but as a working window. It acknowledges limits openly. There are places that cannot yet be reached by observation, not because technology is lacking, but because the structure of space-time itself prevents information from arriving. No telescope, no matter how advanced, can see beyond a horizon that light itself cannot cross. This does not mean science is defeated. It means science is precise about what questions it can answer. Asking what lies beyond the observable universe is not meaningless, but it requires careful framing. Scientists can test whether physical laws appear consistent across vast distances. They can model how space expands and how horizons form. They can infer, cautiously, what unseen regions might be like, while remaining clear about the difference between inference and observation. There is gentle humour sometimes shared among cosmologists about the universe being under no obligation to make sense to human intuition. At these scales, common sense is an unreliable guide. Words become tools rather than reflections of experience. Definitions are chosen not because they feel right, but because they work. They allow predictions to be made, data to be compared, and disagreements to be resolved through evidence rather than impression. In this way, the scientific meaning of the universe is not smaller or colder than the poetic one. It is simply more careful. It leaves room for wonder by resisting overstatement. It replaces dramatic edges with quiet horizons. It turns absolute claims into measured descriptions. And it accepts that the largest questions often come with answers shaped not by certainty, but by clarity about what is known, what is unknown, and where the boundary between the two gently rests. At the largest scales imaginable, understanding begins not with grand declarations, but with precise words, patiently chosen and always open to revision as the universe continues to reveal itself slowly and without hurry. The observable universe is not a special place set aside by nature. It is not a chosen region, nor a boundary drawn with intent. It is simply the part of the universe that can be seen, in principle, from this location, given the rules that govern light, time, and space. Its limits are not defined by matter stopping or space ending, but by how long the universe has existed and how quickly information can travel. Light does not arrive instantly. Every beam carries a history. When light leaves a distant galaxy, it begins a long journey across expanding space. By the time it reaches a telescope, it has already spent billions of years in transit. To look far away is to look back in time. This is why distance and time are inseparable in cosmology. The farther something is, the older the light that reveals it. Because the universe has a finite age, there has only been a finite amount of time for light to travel. Even if the universe extends far beyond what can be seen, only a portion of it has had enough time to send information here. That portion is what scientists call the observable universe. It is a region defined by patience rather than borders, a sphere of visibility shaped by the quiet ticking of cosmic time. This idea can feel counterintuitive. In everyday experience, distance and time are separate ideas. A mountain is far away, but it exists now. A memory happened long ago, but it did not move. In the universe at large scales, these ideas merge. Looking outward is also looking backward. Every observation is a glimpse of an earlier moment, preserved in travelling light. This means the observable universe is not a static object. It changes as time passes. As the universe grows older, light from more distant regions has time to arrive. In that sense, the observable universe expands, not because space itself is growing in this context, but because the window of visibility widens. More history becomes accessible. At the same time, there are limits that no amount of waiting can overcome. Because space itself is expanding, some regions are moving away so quickly that their light will never arrive here, no matter how long one waits. These regions exist, but they are permanently beyond observation. This introduces a quiet but profound idea. Existence and observability are not the same thing. Observation then becomes a defining constraint on knowledge. Science relies on signals, light, radiation, particles, gravitational effects. If something leaves no detectable trace, it cannot be studied directly. This does not mean it is imaginary. It means it lies beyond the reach of current or even fundamental limits of measurement. The observable universe is a practical boundary, not a philosophical one. Modern astronomy has worked carefully to approach that boundary. Over the past several decades, space telescopes have been aimed at seemingly empty regions of sky, areas chosen not because they were interesting, but because they were quiet. Few nearby stars, minimal interference, long exposures, patient collection of faint light. The result of these deep field observations was quietly astonishing. What appeared empty at first glance resolved into thousands of distant galaxies, each one a collection of stars, gas, dust, and history, some so far away that their light began its journey when the universe was young, before familiar structures had fully formed. These images did not show the edge of the universe, they showed the edge of our ability to see. Beyond the faintest detectable glow, darkness returned. Not because nothing exists there, but because the light has not arrived, or never will. The darkness at the edge of deep field images is not a wall, it is a silence. Space telescopes such as Hubble and the James Webb Space Telescope have extended this reach dramatically. By operating above Earth's atmosphere, they avoid distortion and interference. By observing in different wavelengths, they capture light that would otherwise remain hidden. Each technological advance sharpens the picture, pushing observation closer to the earliest times accessible to light. Still, even the most advanced instruments do not provide a complete map. They offer samples, windows, carefully chosen slices of a much larger whole. Astronomers must then piece these observations together, combining data from many directions, distances, and methods to build a coherent model of the universe at large. This is where caution becomes essential. It is tempting to treat observed regions as representative of everything. Often, this is a reasonable assumption, supported by evidence showing large-scale uniformity. But it remains an assumption, tested where possible and acknowledged where it cannot be. Science advances not by claiming completeness, but by clearly stating its limits. There is a gentle irony here. The more precisely scientists define the observable universe, the more clearly they reveal how much lies beyond it. Each improvement in measurement draws a sharper line between what can be known directly and what must remain inferred. This is not a failure of observation, it is a consequence of how the universe behaves. Observation is a powerful tool, but it is not an all-seeing one. It depends on messengers. Light must travel, signals must arrive, time must allow it. Where those conditions are not met, observation stops, even if reality continues uninterrupted. Understanding the observable universe, then, is not about finding a final boundary. It is about learning how knowledge itself is shaped. It shows that the universe does not yield all its information at once. It reveals itself gradually, constrained by time, distance, and expansion. And it reminds us that the darkness beyond what can be seen is not necessarily emptiness, but simply the farthest reach of a very patient light still on its way or forever out of reach. In that sense, the observable universe is less a container and more a conversation between reality and observation, a dialogue conducted in photons, stretched across time, and like any conversation carried over vast distances, it arrives slowly, selectively, and never in full. When cosmologists talk about horizons, they are not imagining walls, shells, or cosmic fences. A horizon is not something you could ever touch, approach, or collide with. It is not made of matter, and it does not mark a sudden change in the fabric of space. A horizon is a limit defined by motion, time, and the flow of information. It is a boundary that exists only in what can be known. One of the most important of these limits is called the particle horizon. This horizon marks the farthest distance from which light has had time to reach this location since the universe became transparent. It is not the farthest thing that exists, but the farthest thing that can be observed so far. Beyond it, light is still travelling, still on its way, or forever prevented from arriving. The particle horizon grows as time passes. Each moment allows light from slightly farther away to complete its journey. In this sense, the horizon is patient rather than fixed. It slowly expands, revealing more of the universe's history layer by layer. What lies just beyond it today may become visible in the distant future, assuming the expansion of space allows that light to arrive. There's another horizon, quieter and more subtle, known as the event horizon. While the particle horizon looks backward, the event horizon looks forward. It marks the farthest distance from which light emitted now will ever reach this location in the future. Because the universe is expanding, and because that expansion is accelerating, some regions are being carried away so quickly that even newly emitted light will never bridge the growing gap. This introduces an unsettling but fascinating idea. There are places in the universe that can be seen today, but will never be seen again. Their light is arriving now, but future light from those same regions will fail to reach us. Over immense spans of time, galaxies can slip beyond the event horizon, not by vanishing, but by becoming unreachable. Neither of these horizons is a physical edge. There is no signpost at the particle horizon announcing the end of space. There is no ripple or seam at the event horizon where the universe changes character. These horizons are invisible limits, defined by relationships rather than structures. They depend on where you are, when you are, and how the universe behaves as a whole. A useful way to think about cosmic horizons is to imagine communication rather than travel. A horizon marks the boundary of possible exchange. Beyond it, signals cannot arrive or depart. This does not mean those regions are cut off from existence. It means they are cut off from interaction, at least with this location. Reality continues, but the conversation ends. Expansion plays a central role in shaping these limits. Space is not a static stage on which objects move. It is dynamic. As space expands, it stretches the distances between distant regions. Light travelling through this expanding space is carried along, its wavelength stretched, its journey lengthened. In some cases, the expansion wins. The distance grows faster than the light can cross it. This is why horizons can form without any barrier at all. Nothing blocks the light. There is no obstruction. The geometry of space-time itself sets the limit. It is a quiet outcome of how distances evolve over time. Understanding these horizons requires careful observation and long-term measurement. Scientists cannot see a horizon directly, but they can infer its presence through patterns. By studying how galaxies are distributed, how their light is redshifted, and how expansion changes over time, cosmologists can calculate where these limits must lie. Data gathered from many missions contribute to this picture. Measurements of distant supernovae help reveal how expansion accelerates. Maps of background radiation show how the universe behaved when it was young. Galaxy surveys chart the large-scale structure of space. Each dataset adds a constraint, tightening the range of possibilities and sharpening the definition of cosmic horizons. What emerges from this collective effort is not a map with a hard boundary, but a set of relationships, distances that can be reached by light, distances that cannot, times beyond which communication fails. Horizons are mathematical consequences of these relationships, grounded in observation and tested across independent measurements. There is a temptation to imagine horizons as places where something dramatic happens. A sudden drop into nothingness, a curtain drawn across the universe. In reality, crossing a horizon would be entirely uneventful. A galaxy moving beyond an event horizon does not explode or fade at the moment it crosses. From its own perspective, nothing special occurs at all. The drama exists only from afar, in the gradual loss of contact. Signals stretch, dim, and eventually fail to arrive. Over time, fewer and fewer distant objects remain visible. The universe becomes quieter, not because it contains less, but because less can be heard. There is a subtle humour in this, though it is the kind that reveals itself slowly. The universe does not hide its secrets behind barriers. It simply keeps moving. It expands, it ages, and in doing so, it carries parts of itself out of reach. The limits arise not from concealment, but from patience exceeding possibility. Cosmic horizons also remind scientists to be cautious with language. Saying that something is beyond the horizon does not mean it is beyond reality. It means it is beyond current or even permanent access. This distinction protects science from overclaiming. It allows models to extend beyond observation without pretending those extensions are directly verified. In this way, horizons serve as both guides and guards. They guide inquiry by showing where evidence can be gathered. They guard against speculation by marking where inference must replace observation. They are not obstacles to understanding, but signposts for humility. At the larger scales, the universe does not end in darkness or collision. It fades into distance, into time, into limits shaped by expansion. Horizons define where knowing gives way to reasoning, and where reasoning must eventually pause. These invisible boundaries do not shrink the universe. They simply define the reach of a single viewpoint within it. And within that reach, remarkably, the universe has proven generous, offering light that has travelled for billions of years, carrying stories from regions long gone, still whispering across expanding space, right up to the edge of what can be known. When scientists say the universe is expanding, they are not describing an explosion sending galaxies flying outward into empty space. There is no central point where everything began rushing away. Instead, expansion refers to the stretching of space itself. Distances between faraway regions increase over time, not because those regions are racing through space, but because the space between them is quietly growing. This idea is one of the most counterintuitive features of modern cosmology. In everyday life, motion means travelling from one place to another. Expansion at cosmic scales works differently. Galaxies can remain nearly at rest relative to their local surroundings, while still becoming more distant from one another overall. Space does the moving for them. The evidence for this stretching comes from light. When astronomers examine the light arriving from distant galaxies, they find that its colour has shifted toward longer wavelengths. This effect is called redshift. The farther away a galaxy is, the more its light appears stretched. This stretching is not caused by the galaxy moving through space in the usual sense, but by space itself expanding while the light is in transit. Redshift acts like a cosmic ruler. It provides a measurable signal that links distance and expansion. Light emitted long ago began its journey with one wavelength and arrived much later with another. The change encodes information about how much the universe expanded during that journey. By studying redshift across many galaxies, scientists can reconstruct how expansion has behaved over time. The discovery of expansion did not happen all at once. In the early 20th century, astronomers were still debating whether distant fuzzy objects were clouds within our galaxy, or entire galaxies of their own. As better telescopes revealed their true nature, measurements of their light began to show a pattern. The farther away a galaxy appeared to be, the more its light was redshifted. This relationship between distance and redshift was one of the first clear signs that the universe was not static. Space itself was changing. Over time, this idea matured from a surprising observation into a central pillar of cosmology. Expansion was no longer a curiosity. It became the framework within which cosmic history was understood. Modern measurements have refined this picture dramatically. Astronomers no longer rely on a single method to track expansion. Instead, they combine many independent approaches. Distances are measured using well-understood astronomical objects. Redshifts are catalogued across millions of galaxies. Patterns in large-scale structure provide additional constraints. Each method checks the others, reducing uncertainty and revealing subtle details. Galaxy surveys play a crucial role here. By mapping the positions and redshifts of vast numbers of galaxies, these surveys create a three-dimensional picture of the universe at different stages in its history. The distribution of galaxies is not random. It carries imprints of how matter clumped together as space expanded. These patterns allow scientists to test models of expansion against real data. Space observatories contribute a different perspective. By observing light that never reaches the ground, they extend measurement into wavelengths blocked by Earth's atmosphere. This allows astronomers to see galaxies that are extremely distant and faint, whose light has been stretched far beyond its original form. Each new observatory adds depth to the picture, pushing observation closer to the early universe. What emerges from all this data is a consistent story. The universe has been expanding for a very long time, and that expansion has not proceeded at a constant pace. Early on, expansion behaved differently than it does today. Later, it began to accelerate. These conclusions are not drawn from a single observation, but from the convergence of many independent lines of evidence. It is important to emphasize what expansion does and does not do. Expansion does not pull objects apart against their will. Local structures such as galaxies, star systems, and even clusters remain bound by gravity and other forces. Expansion becomes noticeable only at very large scales, where the collective stretching of space outweighs local attractions. This explains why expansion can feel abstract. It does not affect daily experience. It does not stretch rulers or disrupt atoms. Its influence becomes clear only when comparing regions separated by immense distances. At those scales, expansion shapes everything from the distribution of galaxies to the limits of observation itself. There is a quiet elegance to this idea. Space is not an empty backdrop. It is an active participant in the universe's story. It grows, it stretches, and in doing so, it shapes what can be seen and what remains forever distant. Expansion is not something happening inside the universe. It is something the universe is doing. Understanding expansion also helps clarify why concepts like edges and boundaries are misleading. If space itself is stretching everywhere, then there is no outer surface where expansion stops. Every region participates equally. The universe does not grow outward from a center. It grows uniformly, carrying all distant regions away from one another. This has practical consequences for observation. As space expands, light travelling through it is stretched. Its energy changes. Its ability to convey information diminishes over vast distances. Expansion, therefore, directly shapes the observable universe. It determines which signals arrive and which fade away before reaching us. Despite its abstract nature, expansion is one of the best tested ideas in cosmology. It is supported by decades of observation, refined by increasingly precise instruments, and continually checked against new data. When measurements disagree, scientists do not discard expansion. They examine assumptions, refine models, and improve observations. The core idea remains robust. There is also room for humour in how expansion defies expectation. The universe, it turns out, does not behave like a tidy container with fixed dimensions. It behaves more like a story that keeps adding pages, not at the end, but everywhere at once. Distances increase, not because things are rushing off stage, but because the stage itself is slowly growing. Expansion is not something to imagine visually as a single event. It is better thought of as a process, ongoing and relentless, shaping cosmic history moment by moment. It links the past to the present and sets the conditions for the future. It explains why distant galaxies appear the way they do and why some regions will never be seen again. In the end, the expansion of space is less about motion and more about relationship. It describes how every part of the universe relates to every other part over time. It reminds us that space is not passive. that distance is dynamic and that the universe is not static scenery, but a living structure whose very geometry evolves, slowly and without pause. In the earliest moments of the universe, before stars formed and before galaxies took shape, space itself may have behaved in an unusual way. According to a widely studied idea in cosmology, the universe experienced a brief period of extremely rapid expansion known as inflation. This phase is thought to have occurred very early on, long before the universe settled into the slower expansion observed today. Inflation is not proposed as a dramatic explosion or a burst of energy flinging matter outward. Instead, it describes a rapid stretching of space itself. Distances between regions increased enormously in a very short amount of time. Regions that were once close enough to interact were suddenly carried far apart, embedded in a universe that became vast almost instantly. The idea of inflation arose not from a desire for drama, but from a need for consistency. When scientists study the large-scale structure of the universe, they notice several puzzling features. The universe appears remarkably uniform in all directions. Distant regions that have never been in contact look strikingly similar. Space also appears very close to geometrically flat, rather than strongly curved. Inflation was proposed as a way to explain these observations with a single underlying process. If inflation occurred, it would mean that the observable universe is only a small part of a much larger whole. The region that can be seen today would have originated from an even smaller patch of space before inflation began. That patch was then stretched to enormous size, carrying its properties across a much larger expanse. Beyond the observable region, space would continue, shaped by the same expansion, but forever beyond direct observation. This is why inflation naturally suggests vast regions beyond what can be seen. If space expanded rapidly and uniformly, there is no reason to think it stopped neatly at the edge of visibility. The observable universe becomes a window into a much larger reality, not because that reality is hidden, but because it expanded beyond the reach of light long ago. Inflation also helps explain why distant regions look so similar. Before inflation, these regions were close enough to share information and reach similar conditions. After inflation, they were separated by immense distances, carrying those shared properties with them. What appears mysterious today may have been quite ordinary before space grew so dramatically. Evidence for inflation does not come from seeing it directly. Instead, it comes from subtle patterns imprinted on the universe during its earliest moments. One of the most important sources of this evidence is the faint background radiation that fills all of space. This radiation is the cooled remnant of an early, hot phase of the universe, now stretched into long wavelengths by expansion. This background radiation is remarkably uniform, but not perfectly so. Tiny variations in its temperature appear across the sky. These variations are extremely small, yet they carry a wealth of information. They reflect minute differences in density present in the early universe, differences that later grew into galaxies and large-scale structure. Inflation provides a natural explanation for these patterns. During the inflationary phase, tiny quantum fluctuations would have been stretched to cosmic scales. These fluctuations became the seeds for later structure, leaving their imprint on the background radiation. The specific statistical properties of these variations match well with predictions made by inflationary models. Several satellites have played a crucial role in measuring this background radiation with increasing precision. Early missions established its existence and overall uniformity. Later satellites mapped its tiny variations across the entire sky. Each improvement in resolution and sensitivity refined the picture, allowing scientists to test inflationary predictions more carefully. The results have been strikingly consistent. the patterns observed align closely with what inflation predicts, within the limits of measurement. This does not prove inflation beyond all doubt, but it provides strong support for the idea. It shows that inflation is not just an abstract proposal, but a theory grounded in observable consequences. At the same time, inflation remains an area of active research and debate. There are many versions of inflationary models, each differing in details about how inflation began, how long it lasted, and how it ended. Observations help narrow these possibilities, but they do not yet single out a unique answer. Inflation explains much, but not everything. This uncertainty is not a weakness. It reflects the scale of the problem. Inflation deals with conditions far beyond anything that can be recreated or observed directly. It reaches into a regime where familiar physics blends into unknown territory. Caution is not only sensible here, it is essential. One of the intriguing consequences of inflation is the possibility that it did not occur just once. Some versions of the theory suggest that inflation could happen repeatedly in different regions of space, creating a patchwork of expanding domains. Each domain could have its own observable universe, separated from others by distances that cannot be crossed. This idea is discussed carefully and without exaggeration. It arises naturally in some theoretical frameworks, but remains difficult to test. Whether or not such scenarios reflect reality, they highlight how inflation stretches the concept of the universe beyond intuitive boundaries. The observable region becomes a local sample rather than the whole story. There is a gentle irony in how inflation reshapes understanding. A theory introduced to explain uniformity ends up suggesting extraordinary vastness. A process meant to smooth out differences leads to a universe where much lies permanently unseen. Inflation does not reduce mystery, it relocates it. The early universe shaped by inflation was not quiet or static. It was dynamic, rapidly evolving, and governed by conditions unlike anything experienced later. Yet traces of that era remain, stretched thin but still detectable. By studying these traces, scientists reconstruct events that occurred when the universe was unimaginably young. Inflation also reminds us that observation has limits rooted in history. The universe carries a memory of its earliest moments, but that memory is encoded subtly. It must be decoded with care, patience, and precision. Satellites that mapped early radiation did not reveal a picture of the universe at birth, but a fossil record, preserved and transformed by time. There is room for some humour in all this. The universe, it seems, grew up very quickly, expanded dramatically, and then spent the rest of its existence slowly revealing what happened in its earliest moments. Inflation was brief, but its consequences are enormous and enduring. In considering inflation, scientists do not claim to have witnessed the beginning of everything. They offer a framework that connects observation to theory, tying present-day measurements to ancient processes. Inflation stands as one of the most ambitious ideas in cosmology, not because it answers every question, but because it connects so many pieces of the puzzle. Ultimately, inflation shapes how the early universe is understood and why so much lies beyond observation. It suggests that what can be seen is only a fraction of what exists, and it does so not by invoking mystery for its own sake, but by following the evidence left behind by light that has travelled for billions of years, carrying whispers from a time when space itself was learning how to stretch. The idea of an edge feels natural. In everyday life, most things have one. A table ends, a road stops, a page runs out of space. When thinking about the universe, it is tempting to carry that intuition outward and imagine a final boundary where everything simply comes to a halt. But in cosmology, the word edge turns out to be more of a linguistic shortcut than a physical feature. When scientists discuss an edge of the universe, they're rarely suggesting a literal ending to space. There is no cliff where galaxies suddenly stop, no wall marking the last permissible location. Instead, the word edge is often used as a stand-in for something more subtle, a limit to what can be observed, a boundary in knowledge rather than a boundary in reality. This distinction matters because boundaries and limits are not the same thing. A boundary implies something physical. It suggests a separation between regions, a place where one thing ends and another begins. A limit of observation, on the other hand, is defined by conditions. It depends on time, distance, expansion, and the behavior of a light. It tells us how far information can travel, not how far space extends. Scientific models are built with this difference firmly in mind. When cosmologists describe the large-scale structure of the universe, they do not draw boxes around it. They do not cap it with surfaces or enclose it in containers. Instead, they work with geometries that can be finite or infinite without requiring an edge at all. One helpful example comes from geometry rather than astronomy. A sphere has a finite surface area but no edge. You can travel across it indefinitely without ever encountering a boundary. There is no place where the surface suddenly stops. In a similar way, some models of the universe allow space to be finite in extent while still having no edges. Space curves back on itself, gently and consistently, without needing an endpoint. Other models allow space to be infinite, extending endlessly in all directions. In these cases, the idea of an edge simply does not apply. There is no outermost region. Every location is surrounded by more space, and every direction leads onward without conclusion. In both types of models, the familiar notion of an edge fails quietly. So why does the idea persist so strongly? Partly because human intuition is shaped by small scales. Brains evolved to navigate terrain, not space-time. On Earth, limits usually correspond to physical features. At cosmic scales, limits arise from different causes entirely. Expansion, light travel time, and the age of the universe shape what can be known, without placing a fence around existence. This is why scientists are careful when communicating these ideas. Public explanations often rely on metaphors, because raw equations and abstract geometry are not especially soothing listening material. Words like edge and boundary help convey the idea that there is a point beyond which observation fails. But they are used with caution, always accompanied by clarification when space allows. Cosmologists regularly emphasize that the observable universe is not the same as the entire universe. What appears to be an edge is really a horizon, a point beyond which light has not had time to arrive. That horizon moves as time passes. It is not fixed. It doesn't mark a permanent feature of space itself. Scientific models deliberately avoid literal walls because walls introduce problems. A wall would need an explanation. What is it made of? Why is it there? What lies beyond it? How does it interact with the rest of the universe? Introducing a boundary creates more questions than it answers. By contrast, horizons arise naturally from the behavior of space-time and require no additional structure. There is also an observational reason to avoid walls. No evidence suggests their existence. Telescopes do not see a thinning of matter toward a final shell. Background radiation does not show signs of reflection or termination. Large-scale surveys reveal uniformity rather than abrupt endings. The universe looks consistent in all directions as far as measurements can reach. That consistency is one of the strongest arguments against a literal edge. If space had an ending nearby, its effects would be noticeable. Light would behave differently. Structures would change. Patterns would distort. Instead, observation shows smoothness and continuity, limited only by distance and time. Communicating this to the public is a delicate balance. On one hand, the idea that the universe has no edge can feel unsatisfying. It denies a neat conclusion. On the other hand, the idea that what looks like an edge is actually a limit of knowledge can be quietly profound. It reframes the question from where does the universe stop to how does knowing work at the largest scales. Cosmologists often use careful phrasing to guide this shift. They speak of horizons, reach, visibility, and access. These words emphasize process rather than structure. They suggest that limits arise from conditions, not from construction. The universe does not end, observation does. There is a hint of lightness in how stubborn the edge idea can be. Even after decades of explanation, people still ask what is on the other side. It is a reasonable question, rooted in experience. Scientists respond not by dismissing it, but by translating it. There may not be an other side in the usual sense. There may only be regions too distant to interact. This does not make the universe less interesting. If anything, it makes it more subtle. The absence of an edge does not flatten mystery, it spreads it out. Instead of concentrating wonder at a single boundary, it distributes it across the entire expanse of space and time. Scientific models, by avoiding literal walls, leave room for both humility and curiosity. They acknowledge that there are questions that cannot be answered by observation alone. They also show that those limits are not arbitrary. They emerge naturally from the way the universe evolves. When people imagine standing at the edge of the universe, peering into whatever lies beyond, they are really imagining standing at the edge of knowledge. That edge moves. It depends on when and where you are. It shifts with every improvement in measurement and every passing moment of cosmic time. In that sense, the universe does not present itself as a finished object with a final border. It presents itself as a system with rules. Those rules define what can be seen, what can be inferred, and what remains out of reach. The word edge becomes a placeholder for that transition. By understanding why the edge is a metaphor, it becomes possible to ask better questions. Not what stops the universe, but what shapes our view of it. Not where space ends, but how observation begins and ends. These questions may feel less dramatic, but they're far more faithful to what the universe actually offers. And perhaps that is the quiet lesson hidden inside the edge idea. The universe does not close itself off with barriers. It simply asks patience, precision, and a willingness to accept that some limits are not walls to be broken through, but horizons to be understood. When cosmologists talk about the shape of the universe, they are not picturing it from the outside. There is no vantage point floating beyond space, sketching its outline. Instead, shape in this context refers to how space behaves internally, how distances add up, how paths curve, how geometry works when stretched across the largest scales imaginable. Curvature is the key idea here. In everyday life, curvature is easy to spot. A ball curves outward, a bowl curves inward, a flat table does neither. Space, it turns out, can behave in similar ways, though the effects only become noticeable across enormous distances. Locally, space appears very close to flat. Walk across a room, look at the sky, or measure a triangle on Earth, and familiar rules apply. It is only when measurements span vast cosmic scales that curvature, if present, would reveal itself. Cosmologists describe three broad possibilities for the universe: a closed universe, an open universe, and a flat universe. These terms sound simple, but they describe deep geometric behavior rather than physical containment. A closed universe has positive curvature. In such a universe, space curves back on itself, much like the surface of a sphere. Travel far enough in a straight direction, and in principle, you could return to your starting point without ever encountering an edge. An open universe has negative curvature. Space spreads outward in a way that never quite closes back. Parallel paths slowly diverge. Triangles have angle sums less than what everyday geometry would suggest. Space extends endlessly. with no boundary and no looping back. A flat universe sits precisely between these two extremes. Space follows the familiar rules of Euclidean geometry. Parallel paths remain parallel. Triangle angles add up as expected. Flat does not mean small or featureless. It simply means that, on the larger scales, space does not curve inward or outward overall. Each of these possibilities has different implications for whether the universe is finite or infinite. A closed universe is finite but unbounded. It has a limited volume, yet no edge. An open universe is infinite. A flat universe can be either finite or infinite, depending on its overall topology. This is where shape and topology quietly part ways. Topology describes how space is connected, not how it curves locally. Two spaces can have the same curvature and still be connected in very different ways. A simple example is a video game world where moving off one edge of the screen brings you back on the opposite side. The surface is flat, but the connections wrap around. Similarly, the universe could be finite and flat at the same time, looping back on itself in ways that are difficult to visualize but mathematically consistent. What matters for observation is not what space looks like from nowhere, but how it behaves from within. Cosmologists test these ideas by making careful measurements and comparing them to predictions. One of the most powerful tools for this is the faint background radiation that fills all of space, left over from an early hot phase of the universe. This background radiation carries subtle patterns. Tiny variations in temperature are spread across the sky. The size and distribution of these variations depend on the geometry of space. If space was strongly curved, these patterns would appear distorted in characteristic ways. By measuring them precisely, scientists can place limits on how curved space can be. Multiple space missions have contributed to this effort, mapping the background radiation in ever greater detail. The results have been remarkably consistent. Within the limits of measurement, space appears very close to flat. Not exactly flat in an absolute sense, but flat enough that any curvature must be extremely small across the observable region. This does not mean the universe must be infinite. It means that if it is curved, the curvature is gentle enough to escape detection so far. A very large closed universe can appear flat over the portion that can be observed, just as Earth's surface looks flat when standing in a small field. Curvature becomes obvious only when enough of the surface is seen at once. This introduces a quiet humility into cosmology. Observations can rule out strong curvature, but they cannot easily distinguish between a perfectly flat infinite universe and a very large finite one. Both remain consistent with current data. The universe could be vast beyond imagination, and still curve back on itself far beyond the reach of light. There is a subtle elegance in this uncertainty. The universe does not demand that its full shape be known. It allows models that fit the data while leaving room for multiple possibilities. Curvature becomes a constraint rather than a declaration. Topology becomes an open question rather than a solved problem. From a communication standpoint, these ideas are often simplified, sometimes too much. Flat can sound boring, closed can sound claustrophobic, open can sound lonely. In reality, none of these descriptions capture the richness of what they represent. They are technical terms describing how geometry behaves, not emotional states of the cosmos. Cosmologists work carefully to convey this nuance. They emphasize that flat does not mean empty or featureless. A flat universe can still contain vast structure, intricate patterns, and deep history. Curvature is about large-scale geometry, not local complexity. There is also a touch of soft humour in how precise the universe seems to be. Measurements suggest space is balanced almost perfectly between curving inward and curving outward. It is as though the universe chose the most mathematically neat option, not out of preference, but as a consequence of its early evolution. Understanding shape, curvature, and topology helps clarify why the universe does not need an edge. Space can be finite without boundaries. It can be infinite without spilling into anything else. It can loop, stretch, and connect in ways that defy everyday intuition while remaining internally consistent. At the largest scales, the universe is not a box with walls. It is a geometric structure governed by rules. Those rules allow space to have shape without borders and size without edges. They replace the idea of an ending with the idea of connection. By studying how light spreads, how patterns repeat, and how geometry behaves across immense distances, cosmologists continue to narrow the possibilities. Each measurement sharpens the picture, even as it preserves uncertainty. The universe reveals its shape not by showing itself from the outside, but by leaving subtle clues within. In the end, shape and curvature do not tell us where the universe stops. They tell us how it holds together. They describe the quiet architecture of space itself, an architecture that may be finite or infinite, looping or endless, but always governed by geometry rather than walls. When modern telescopes look deep into space, they are not scanning for edges or boundaries. They're collecting faint traces of light, patiently arriving from enormous distances. What these instruments actually see is not the universe as it is now, but the universe as it was, preserved in travelling photons that have crossed expanding space for billions of years. One of the most powerful techniques astronomers use is called a deep field observation. Rather than sweeping across the sky, a telescope is pointed at a single, seemingly empty patch and left to observe it for a very long time. Hours turn into days, days into weeks. Light that would normally go unnoticed slowly accumulates on the detectors. What begins as darkness gradually fills with structure. The results of these observations have been quietly transformative. Regions of sky that appeared empty through smaller instruments reveal themselves to be crowded with distant galaxies. Not dozens, but thousands. Each one a massive system of stars, gas, dust, and dark matter. Each one a record of cosmic history, frozen at the moment its light began the journey toward us. These deep-field images are not special because they show rare places. They are special because they show ordinary places at extreme distances. Wherever the telescope looks deeply enough, galaxies appear. This tells scientists something important. The universe is not clumpy only nearby and sparse far away. It is richly structured across vast scales, at least as far as observation can reach. How far back can modern instruments see? The answer depends on wavelength, sensitivity, and patience. Light from the earliest galaxies has been stretched by expansion into longer wavelengths, often beyond what the human eye can detect. This is where space telescopes become essential. By observing above Earth's atmosphere and across a wide range of wavelengths, they extend vision into the deep past. The Hubble Space Telescope played a crucial role in this effort. Over many years, it captured deep field images that revealed galaxies from a time when the universe was only a small fraction of its current age. These observations reshaped understanding of galaxy formation, showing that structure emerged earlier and more rapidly than once expected. More recently, the James Webb Space Telescope has pushed this boundary even farther. Designed to observe infrared light with extraordinary sensitivity, it can detect galaxies whose light has been stretched dramatically by expansion. Some of the objects it observes formed when the universe was very young, their light arriving after a journey spanning most of cosmic history. What these telescopes show is remarkable, but equally important is what they do not show. They do not reveal a beginning. They do not show a first moment. They do not display an edge where space ends. Instead, they reveal a gradual transition. As observations reach farther back, galaxies become smaller, less organized, and more primitive. Eventually, individual galaxies fade from view, replaced by diffuse glow and background radiation. This fading is not a sign that nothing existed before. It is a sign that light from earlier times has been stretched and scattered beyond detectability in those wavelengths. The instruments reach a point where the universe becomes opaque to direct observation of individual objects. Beyond that point, other methods are required. Deep field images also remind scientists of an important limitation. They show only what lies along a narrow line of sight. Each image is a tiny sample of the sky. Even the deepest observations cover a region smaller than the area of the Moon as seen from Earth. To understand the universe as a whole, astronomers must combine many such observations, gathered from different directions and distances. There is a quiet discipline to this work. Telescopes do not reveal truth in a single dramatic glance. They accumulate evidence slowly. Each photon counts. Each detection is weighed against noise, uncertainty, and alternative explanations. What emerges is not a photograph of the universe in its entirety, but a carefully constructed picture assembled from many pieces. These observations also show the importance of humility. Even the most advanced telescopes do not see everything. There are limits imposed by physics itself. Light can be absorbed. Wavelengths can stretch beyond detection. Expansion can carry regions out of reach entirely. No instrument, no matter how sophisticated, can bypass these constraints. Yet within those limits, telescopes have been extraordinarily generous. They have shown that the universe was already busy early on. Stars formed, galaxies assembled, heavy elements were forged, structure emerged quickly from an initially smooth state. These discoveries have refined theories and sometimes forced revisions, but always within a framework guided by observation. There is also a subtle humour in how much effort is required to see what appears, at first glance, to be nothing. A deep field image often begins as a blank patch. Only after careful explanation does it become clear that every speck is a galaxy, every blur a system of billions of stars. The emptiest looking places turn out to be among the most crowded. Modern telescopes show that observation is not about sweeping gestures. It is about patience. It is about understanding that the universe reveals itself slowly, one photon at a time. What is seen depends on where one looks, how long one waits, and what wavelengths are collected. They also show that seeing farther does not necessarily mean seeing everything. Each improvement in technology sharpens the view, but also clarifies where the view must stop. Telescopes push against the limits of visibility, but they do not erase those limits. Instead, they define them more precisely. In doing so, modern telescopes help reframe questions about the universe. Rather than asking where space ends, they encourage asking how far light can travel. Rather than searching for a final boundary, they reveal a series of fading transitions, each marking a shift in what can be directly observed. What these instruments ultimately provide is not an answer to what lies beyond the observable universe, but a clear picture of how observation itself works. They show that the universe does not present a sharp edge to be photographed. It offers a gradual dimming, a soft horizon shaped by expansion, time, and the finite speed of light. And within that horizon, modern telescopes have revealed a universe rich, structured, and far older than intuition suggests. Beyond it lies not emptiness, but the continuation of a story that light has not yet finished telling and may never tell in full. Long before the first stars ignited and long before galaxies took shape, the universe was filled with light. Not the kind of light that outlines planets or sparkles from stars, but a hot, dense glow that permeated everything. Space was so energetic that light could not travel freely. Photons scattered constantly, trapped in a fog of charged particles. The universe at that time was bright but opaque. As the universe expanded and cooled, a quiet transition occurred. matter settled down just enough for light to finally move without interruption. When that happened, photons were released in every direction, free to travel through space for the first time. Those photons are still traveling today. They fill the universe, arriving from all directions, carrying a snapshot of the universe as it was at that moment. This ancient light is known as the cosmic microwave background. It is not concentrated in one place. It does not come from a single object. It surrounds everything, evenly and persistently. Wherever one looks in the sky, this background glow is present, faint but measurable, stretched into long wavelengths by billions of years of expansion. Calling it a snapshot is useful, but it requires care. This is not a photograph in the usual sense. It is more like a freeze frame taken when the universe was very young. The light shows conditions at a specific cosmic moment, long before stars and galaxies dominated the scene. It marks the earliest time from which light can travel freely to us. One of the most striking features of this background radiation is its uniformity. In every direction, its temperature is almost the same. This remarkable smoothness tells scientists that the early universe was highly uniform. Conditions were nearly identical across vast regions, even those that are now separated by immense distances. Yet the background is not perfectly uniform. Tiny variations exist, incredibly small differences in temperature spread across the sky. These variations are subtle, but they matter enormously. They represent slight differences in density present in the early universe. Over time, gravity amplified those differences, leading to the formation of galaxies, clusters, and the large-scale structure seen today. The discovery of this background radiation was accidental. Early measurements detected an unexpected signal that appeared no matter where instruments were pointed. At first, it was treated as noise. Only later did it become clear that this faint glow was cosmic in origin, a relic of the universe's early state. Once its significance was recognized, dedicated missions were launched to study it in detail. Early satellites confirmed its uniform presence. Later missions mapped its temperature variations across the entire sky with increasing precision. Each new map refined understanding, revealing finer structure and reducing uncertainty. These missions transformed cosmology from a largely theoretical field into a precision science. By analysing the patterns in the background radiation, scientists could infer key properties of the universe, its overall geometry, the amount of ordinary matter, the presence of dark matter and dark energy, even subtle details about how the universe evolved from its earliest moments. The background radiation also provides strong evidence for the idea that the universe has no simple edge. The light arrives from all directions with similar properties. There is no preferred direction, no sign of a nearby boundary or a symmetry. The universe appears the same, statistically, no matter where one looks. At the same time, this light marks a practical observational boundary. It represents the earliest moment from which electromagnetic radiation can reach us. Before that time, the universe was opaque. Photons could not travel freely. No telescope, no matter how advanced, can see beyond this point using light alone. This makes the cosmic microwave background a kind of horizon. Not a wall, but a limit. It defines how far back direct observation can reach. Everything earlier must be studied indirectly, through theory and inference rather than direct imaging. There is a quiet elegance in this boundary. It is not arbitrary. It arises naturally from the physics of the early universe. As the universe expanded and cooled, conditions changed, allowing light to decouple from matter. That transition left behind a uniform glow that now serves as both a record and a limit. Studying this background also requires extraordinary care. The signal is faint. It must be separated from foreground sources, including emissions from our own galaxy and nearby objects. Sophisticated data processing techniques are used to isolate the cosmic signal, ensuring that what is measured truly reflects the early universe. Despite these challenges, the consistency of results across multiple missions is striking. Independent instruments, using different technologies, have produced maps that agree closely with one another. This agreement builds confidence that the patterns seen are real and not artifacts of measurement. There is a subtle humour in the idea that some of the most important information about the universe comes from something so quiet. The cosmic microwave background is not bright to human eyes. It does not dazzle or sparkle, it whispers. Yet within that whisper lies a detailed account of the universe's infancy. The background radiation also reshapes how questions about beginnings are framed. It does not show the birth of the universe itself. It shows a moment after which the universe became transparent. It is a boundary of visibility, not a boundary of existence. This distinction matters when thinking about what lies beyond observation. The background radiation does not imply that nothing existed before it. It implies that light from earlier times cannot reach us directly. The universe may have been active, dynamic, and complex long before this snapshot was taken. Its earlier story is simply harder to read. In this way, the cosmic microwave background acts as both a gift and a reminder. It offers a detailed window into the early universe, revealing conditions that shaped everything that followed. At the same time, it reminds us that observation has limits, defined not by technology alone, but by the fundamental behavior of space and time. The universe has left behind a record of its youth, stretched thin across the sky. By studying it, scientists have learned not only about the early universe, but about the structure and fate of the cosmos as a whole. And by recognizing where this record begins, they also recognize where direct observation must end. Beyond that boundary, questions remain open, but within it, the cosmic microwave background stands as one of the clearest, calmest signals the universe has ever offered. A steady glow from a time when everything was closer, hotter, and just beginning to unfold. For much of the 20th century, astronomers assumed that the expansion of the universe was slowing down. Gravity, after all, pulls things together. With enough matter spread across space, it seemed reasonable to expect that expansion would gradually decelerate, even if it never fully reversed. The universe might keep expanding, but more and more reluctantly, like a stone thrown upward under gravity. That expectation made the discovery that followed all the more surprising. In the late 1990s, teams of astronomers studying distant stellar explosions noticed something odd. Certain supernovae used as reliable distance markers appeared dimmer than expected. These explosions were not nearby. Their light had travelled for billions of years before reaching Earth. By comparing how bright they should have been to how bright they actually appeared, astronomers could estimate how the expansion of the universe had changed over time. The results pointed to a startling conclusion. The expansion of the universe was not slowing down. It was speeding up. This idea of accelerated expansion was unexpected enough that it was tested relentlessly. Different teams used different samples. Independent analyses were performed. Alternative explanations were explored. Yet the result persisted. The universe was not just expanding. It was accelerating. The evidence came primarily from surveys of a particular type of stellar explosion known for its consistency. These explosions reach nearly the same peak brightness each time, making them useful for measuring cosmic distances. By observing many of them at different distances, astronomers could reconstruct how expansion behaved at different stages in cosmic history. What they found was clear. Long ago, expansion behaved differently. More recently, something began pushing space to expand faster and faster. Gravity alone could not account for this behavior. A new component appeared to be influencing the universe on the larger scales. This unknown influence came to be called dark energy. The name is descriptive rather than explanatory. It does not tell us what dark energy is. It simply labels the effect that causes accelerated expansion. In that sense, dark energy is less a substance than a placeholder for something not yet fully understood. Despite its mysterious name, dark energy has very real consequences. It changes how the universe evolves. It alters how distances grow over time, and crucially, it reshapes what will remain observable in the far future. As expansion accelerates, distant regions of the universe are carried away more rapidly. Light travelling toward us from faraway galaxies must cross an ever-growing expanse of space. In some cases, it never succeeds. Galaxies that are visible today may eventually fade from view, not because they cease to exist, but because the space between us and them expands too quickly. This means the observable universe is not only shaped by the past, but by the future. There are regions that can be seen now but will become unreachable later. Over immense timescales, the night sky will grow quieter. Fewer galaxies will remain visible. The cosmic landscape will appear emptier, even though the universe itself continues to exist beyond view. Dark energy effectively places a horizon on the future. Not a sharp boundary, but a gradual one. A limit beyond which information emitted today will never arrive. This horizon defines what can be known not just now, but ever. Understanding dark energy has therefore become one of the central goals of modern cosmology. Observations continue, not only of supernovae, but of galaxy distributions, background radiation, and large-scale structure. Each method probes expansion in a different way, offering independent checks on the same underlying phenomenon. Large observational programs map millions of galaxies to trace how structure has grown over time. Patterns in these maps reveal how expansion influences the clumping of matter. Background radiation measurements provide a snapshot of earlier conditions, allowing comparison between early and late cosmic behavior. Together, these observations form a consistent picture of accelerated expansion. Future observation programs aim to refine this picture further. New telescopes and surveys are designed to measure expansion with greater precision, reduce uncertainties, and test whether dark energy behaves consistently across time. Some programs focus on gathering enormous data sets. Others aim for extremely precise measurements of smaller samples. Both approaches are necessary. There is an important nuance here. Dark energy does not pull things apart locally. Galaxies remain bound. Stars continue to orbit. Even clusters of galaxies hold together under gravity. Dark energy becomes dominant only at very large scales, where the cumulative stretching of space outweighs local forces. This subtlety can make dark energy feel abstract. It does not announce itself in daily experience. Its effects are revealed only through careful measurement across vast distances and long timescales. It shapes the universe quietly, persistently, and without spectacle. There is also a slight touch of humour in how dark energy behaves. Despite its dramatic impact on cosmic fate, it leaves almost no direct trace. It does not clump, it does not glow, it does not interact in familiar ways. It influences the universe simply by being there, evenly distributed, nudging space to expand faster as it grows more dominant over time. From a communication standpoint, dark energy is often misunderstood as a force pushing galaxies apart. In reality, it is better thought of as a property of space itself, influencing how expansion unfolds. This distinction matters because it avoids the image of galaxies being flung outward by some invisible hand. Space expands, and dark energy affects how that expansion proceeds. The discovery of accelerated expansion also changed how scientists think about the ultimate fate of the universe. If expansion continues to accelerate, distant regions will become increasingly isolated. Over time, the observable universe will shrink in practical terms, even as space itself grows larger. This future isolation highlights the importance of present observation. The universe is most observable now, during a brief window when light from many distant regions is still arriving. In the far future, astronomers may have access to less information than there is available today. Dark energy ensures that some cosmic knowledge has an expiration date. This realization adds a quiet poignancy to cosmology. The universe is not only vast and ancient, it is also fleeting in what it reveals. Observation is constrained not just by technology, but by cosmic timing. Dark energy remains one of the deepest open questions in science. Its nature is still unknown. Whether it is truly constant or slowly changing remains under investigation. What matters for now is not having a final answer, but recognizing its role in shaping the universe we observe. The accelerated expansion it drives does not create an edge in the traditional sense. It creates horizons. It redraws the boundaries of visibility. It determines which regions remain part of our observable story and which quietly slip beyond reach. In this way, dark energy connects deeply to the question of what lies beyond the observable universe. It does not build walls or define borders. It stretches space in such a way that limits emerge naturally, limits of contact, limits of knowledge, limits of future observation. The universe continues, shaped by forces still being understood. Dark energy ensures that some of it will remain unseen, not because it is hidden, but because the universe itself is expanding too quickly for light to keep up. The universe is often described as revealing more of itself over time, and in many ways that has been true. Telescopes have grown more powerful, observations have reached farther back, knowledge has accumulated steadily. But there is a quieter, less intuitive truth woven into the fabric of cosmic expansion. There is a future in which less of the universe will be visible than there is today. This future edge of observation is not caused by instruments failing or curiosity fading. It is shaped by expansion itself. As space continues to stretch, distances between faraway regions grow ever larger. Light travelling toward us must cross an expanding sea of space, and for some regions that journey becomes impossible. The farther a galaxy is, the more its light is stretched as it travels. Over time, that light becomes fainter and redder, eventually slipping beyond the range that any detector can register. Even if a galaxy continues to shine just as brightly in its own local region, its signal fades from view elsewhere, not because it stops emitting light, but because space expands faster than the light can compensate for. This means that galaxies can slowly disappear from the observable universe. They do not vanish suddenly. There is no dramatic moment when a galaxy winks out of existence. Instead, its light grows dimmer, its features blur, and eventually it becomes indistinguishable from background noise. One by one, distant regions slip beyond detection. This process is already underway. Some galaxies visible today are destined to become unobservable in the far future. As expansion accelerates, the list grows longer. Over immense spans of time, only nearby galaxies will remain within reach. Everything else will recede beyond the future horizon of observation. This has profound implications for observational cosmology. Much of what is known today about the universe relies on the ability to see far away. Distant galaxies reveal how structure formed. Background radiation provides a record of early conditions. Large-scale surveys allow scientists to test models of expansion and geometry. All of this depends on access to ancient light. In the far future, that access will shrink. Observational cosmology, as it exists now, will become increasingly difficult. The evidence used to infer the universe's history will fade from view. Future astronomers may find themselves in a universe that appears smaller, quieter, and less informative than the one observed today. This does not mean future scientists will be less capable. Their instruments may be far more advanced. Their theories may be deeper and more refined. Yet the universe they observe will offer fewer clues. Expansion will have erased many of the signals that currently inform cosmological models. There is an irony here that cosmologists sometimes note with a mix of seriousness and light humour. Humanity happens to exist at a time when the universe is particularly observable. Light from distant regions is still arriving. The background radiation is still detectable. Galaxies are still visible across vast distances. This era of rich observation is not permanent. In the far future, an observer looking up at the sky might see only a small collection of nearby galaxies, bound together by gravity. The rest of the universe would be invisible, not because it ceased to exist, but because expansion carried it beyond reach. From that vantage point, the universe might appear static, isolated, and far simpler than it truly is. Such an observer might reasonably conclude that their local group of galaxies is the entire universe. Without access to distant light, there would be little evidence for expansion, no visible background radiation, and no direct indication of a hotter, denser past. Cosmological conclusions drawn under those conditions would be very different. This possibility has led scientists to reflect on the role of timing in knowledge. Understanding the universe is not only a matter of intelligence and technology, it is also a matter of when observations are made. The universe offers different information at different stages of its evolution. Some eras are more revealing than others. The future edge of observation also reinforces the idea that horizons are not fixed. They depend on cosmic history. As expansion accelerates, the boundary of what can be seen changes. The observable universe is not a static sphere. It evolves, shaped by the balance between light travel and the growth of space. Importantly, this does not imply that the universe itself is shrinking or simplifying. On the contrary, it continues to evolve, form structures, and follow its physical laws. What changes is the ability of one region to observe another. The universe becomes increasingly fragmented into isolated pockets of visibility. From a scientific perspective, this raises interesting questions about inference. How much can be known about the universe from limited data? What assumptions are reasonable when observation is constrained? How can models be tested when key evidence is no longer accessible? These questions are not purely hypothetical. They inform how scientists think about current observations. Knowing that some information will eventually be lost adds urgency to present measurements. It also encourages careful preservation of data and models that future researchers may rely on. There is also a philosophical aspect to this future limitation. The universe does not guarantee that all truths remain accessible forever. Knowledge can be time-sensitive. Some facts about cosmic history may be discoverable only during certain windows of opportunity. Outside those windows, they may be inferred at best, or remain unknown. This does not diminish the value of science. It highlights its contextual nature. Science operates within the universe it studies, subject to the same physical laws and constraints. Its reach is shaped by the cosmos, just as much as its questions are. There is a quiet beauty in this idea. The universe reveals itself gradually, then slowly draws a veil. It does not do so abruptly or cruelly. It simply continues expanding, following its rules, indifferent to who is watching or when. Future scientists may possess remarkable insight into local physics, stellar processes, and planetary systems. Yet their view of the cosmos as a whole may be narrower. They may know less about the large-scale universe than is known today, despite having access to more advanced tools. This possibility encourages a sense of perspective. The current era of cosmology is not just a triumph of technology and theory. It is also a moment in cosmic history when conditions allow a wide view. The universe, for now, is still talkative. As time passes, that conversation will quiet. Distant voices will fade. The observable universe will contract in practical terms, even as space itself grows larger. The future edge of observation will draw closer, not because the universe ends, but because its expansion outruns light. In contemplating this future, cosmologists are reminded that the universe is not obligated to be fully knowable. It offers clues generously for a time, then withholds them, not out of mystery but out of motion. Space expands, horizons form, observation adapts. The universe continues, vast and dynamic, whether or not it can be fully seen. And in that sense, the future edge of observation is not a loss, but a reminder. Knowledge is shaped by circumstance. Understanding is bound to time. And even in a universe without edges, there are limits to what can be known, gently enforced by the quiet, relentless expansion of space itself. Beyond the observable universe lies a region that science acknowledges carefully, speaks about cautiously, and never claims to see. These regions are not hidden behind walls or separated by barriers. They are simply too far away, too distant in space and time for information to reach us. Light from those places will never arrive here. Not now, not later, not ever, given how the universe expands. These permanently unobservable regions are not special or exotic by necessity. They are ordinary parts of the universe that happen to lie beyond the reach of communication. From their own perspective, they are no more central or remote than this location is from ours. The difference is not physical but relational. Space has expanded in such a way that no signal can cross the growing distance between us and them. This idea can feel unsettling at first. It challenges a deeply rooted assumption that with enough technology, enough patience, and enough ingenuity, everything can eventually be observed. In cosmology, that assumption does not always hold. Some limits are not technological. They are built into the structure and history of space-time itself. When scientists talk about what lies beyond the observable universe, they do not imagine a fundamentally different realm by default. Instead, they usually assume physical continuity. The same laws of physics apply everywhere. The same types of particles exist. The same relationships between matter, energy, space, and time hold true. This assumption is not arbitrary. It is based on consistency. Everywhere that has been observed so far, the universe behaves according to the same underlying rules. There is no evidence that physics changes abruptly with distance. No sign that crossing a particular threshold transforms reality. Given this uniformity, the simplest assumption is that regions beyond observation are similar in nature to those within it. This assumption is powerful, but it is still an assumption. It cannot be tested directly. No experiment can be performed on regions that cannot exchange information with us. No telescope can gather light that will never arrive. Science must therefore rely on inference rather than detection when discussing these parts of the universe. Inference works by extending well-tested principles beyond the range of direct observation. If physical laws appear consistent across billions of light years, it is reasonable to expect that they continue to hold elsewhere. This approach has proven reliable in many areas of science. It allows understanding to progress even when direct access is impossible. However, inference is not certainty. Scientists remain careful to distinguish between what is known through observation and what is inferred through reasoning. Beyond the observable universe, conclusions become progressively less secure. Confidence decreases as assumptions accumulate. This is not a flaw. It is an honest reflection of how knowledge is built. There is an important distinction here between saying something cannot be observed and saying it does not exist. Science does not equate invisibility with non-existence. Many things are accepted as real because their effects are observed indirectly. Yet in the case of permanently unobservable regions, even indirect effects may be absent. Those regions do not influence this one in measurable ways. This makes them scientifically quiet. They do not leave traces. They do not distort measurements. They do not announce their presence. Their existence is inferred from the behavior of the universe as a whole, particularly from models of expansion and early cosmic history. One reason these regions are thought to exist at all is the success of models that describe the universe as much larger than the observable portion. Inflationary ideas, for example, naturally lead to a universe far more extensive than what can be seen. In such models, the observable universe becomes a small patch within a vast expanse. Again, this does not mean these models are proven in every detail. It means they provide coherent explanations for observed features while implying consequences that extend beyond observation. Scientists acknowledge those implications without claiming direct evidence for them. There's also a subtle shift in how questions must be framed when discussing the unobservable. Asking what lies beyond the observable universe is not the same as asking what is there in the usual sense. It is closer to asking what can be reasonably assumed given what is known. The answers are conditional, provisional, and open to revision. This approach requires restraint. It is tempting to fill unseen regions with speculation, dramatic structures, or exotic physics. Science resists this impulse by favoring minimal assumptions. Continuity is preferred over novelty unless evidence suggests otherwise. Simplicity is valued, not because the universe must be simple, but because simple explanations are easier to test where testing is possible. There is a quiet discipline in accepting that some regions may remain forever beyond reach. It forces science to confront its own limits. Not all questions can be settled by observation. Some can only be approached indirectly, through consistency, coherence, and the absence of contradictions. This does not make such questions meaningless. On the contrary, they sharpen understanding of what science does and does not claim. They clarify the boundary between empirical knowledge and theoretical extension. They encourage careful language and thoughtful humility. There is also room for humour in the idea that the universe might be far larger than anything that can ever be seen. It suggests a cosmos that does not tailor itself to curiosity. It continues expanding, indifferent to who is watching or what instruments are built. The universe does not hide its farthest reaches out of secrecy. It simply keeps growing. Beyond the observable universe there may be galaxies, stars, planets, and perhaps phenomena entirely unfamiliar. Or there may be nothing but diffuse matter and radiation. Science does not know, and it does not pretend to. What it offers instead is a framework for thinking about such regions responsibly. Inference allows scientists to say that these regions likely exist and likely resemble the parts of the universe already studied. It does not allow detailed descriptions, maps, or narratives. Detection remains out of reach, not because of current limitations, but because of permanent ones. This distinction is crucial. It prevents cosmology from drifting into unfalsifiable claims. It keeps speculation grounded. It ensures that when scientists speak about what lies beyond observation, they do so with clarity about what is known, what is assumed, and what is simply unknown. In the end, the idea of regions beyond the observable universe expands perspective without demanding certainty. It suggests that reality is larger than experience, not because experience is flawed, but because it is local. Every observer occupies a finite position in an immense space-time. The universe does not promise that everything can be seen. It allows knowledge to grow within limits, shaped by expansion, time, and causality. Beyond those limits lies not a forbidden zone, but a continuation of space that remains silent to this location. Science stands at that boundary with patience rather than frustration. It infers carefully, speaks precisely, and accepts that some parts of the universe will never send a message this way. And in doing so, it offers not a complete map, but a clear understanding of how far observation can reach, and why beyond that reach, reasoning must quietly take its place. When the word multiverse appears in discussions of cosmology, it often carries more weight than clarity. In popular culture, it can suggest dramatic alternate realities or countless parallel worlds brushing up against one another. In science, however, the idea is handled far more cautiously. The multiverse is not a single theory, nor a confirmed feature of reality. It is a collection of related ideas that emerge naturally from certain well-established models, particularly those involving the early universe. At its core, the multiverse refers to the possibility that what is commonly called the universe may be only one region within a much larger structure. This larger structure could contain many regions similar to our own, each with its own observable universe, separated by distances or conditions that prevent interaction. Importantly, this idea does not arise from a desire to add mystery. It arises as a consequence of attempting to understand how cosmic expansion behaved in its earliest moments. One of the most discussed multiverse ideas grows out of inflationary cosmology. Inflation was introduced to explain why the universe appears so uniform, and why distant regions share similar properties. Some versions of inflation suggest that the rapid expansion did not occur just once and then stop everywhere. Instead, inflation may have continued in some regions even after it ended locally. In this picture, different regions of space stop inflating at different times. Each region that exits inflation becomes its own observable universe, expanding more slowly and forming galaxies, stars, and structure. Other regions continue inflating, stretching space so rapidly that they remain forever disconnected from those that have settled down. The result is a vast, ever-growing structure containing many separate cosmic domains. These domains are sometimes described as bubble universes. The term is metaphorical, not literal. There are no soap film boundaries or collisions that can be directly observed. The bubbles do not float in a surrounding space in the everyday sense. They are simply regions of space-time that share a common history after inflation ends locally. In such scenarios, the observable universe becomes one bubble among many. What lies beyond its horizon is not emptiness, but more inflating space and perhaps other regions with similar physics. This idea follows logically from certain mathematical treatments of inflation. It is not added on top of the theory, it falls out of it. Despite this, the multiverse remains controversial within science. The primary reason is testability. Science depends on the ability to compare predictions with observations. If other universes are permanently beyond observation, then direct testing becomes impossible. This raises difficult questions about how such ideas should be evaluated. Some scientists argue that if a theory makes successful predictions about observable phenomena, then its unobservable consequences can be taken seriously, even if they cannot be tested directly. Others counter that ideas which cannot be falsified should be treated with extreme caution, regardless of how elegant or natural they appear within a mathematical framework. This debate is ongoing and active. It is not settled, and it is not framed as a conflict between belief and disbelief. It is a methodological discussion about what counts as scientific explanation and how far theoretical extension can reasonably go. There are also different kinds of multiverse ideas beyond inflationary ones. Some arise from attempts to unify physical laws. Others emerge from mathematical considerations about how constants might vary. In each case, the multiverse appears not as a prediction that can be checked, but as a possible interpretation of deeper theories. It is important to emphasize that none of these ideas claim that multiple universes have been observed. They are not conclusions drawn from data in the way expansion or background radiation is. They are discussions about what existing theories might imply when followed to their logical ends. Scientists working on these topics are typically careful to state this distinction clearly. Multiverse ideas are presented as possibilities, not discoveries. They are explored because they may help explain why the universe has the properties it does, not because they provide confirmed answers. One motivation often discussed is the question of why physical constants take the values they do. Some multiverse scenarios suggest that different regions could have different properties, with our observable universe being one where conditions happen to allow complex structures to form. This line of reasoning is treated cautiously and is far from universally accepted. There is a funny irony among cosmologists about how the multiverse captures attention far beyond its evidential status. It is an idea that travels faster than the data supporting it. This is why researchers often emphasize that discussing the multiverse does not mean endorsing it as reality. It means acknowledging that certain theories raise questions that extend beyond observation. From a scientific standpoint, the multiverse remains an open discussion rather than a settled claim. It occupies a space where physics, cosmology, and philosophy overlap. Its value lies not in providing answers, but in highlighting the limits of explanation and the challenges of testing ideas about the largest possible scales. Importantly, rejecting or accepting multiverse ideas does not change what is known about the observable universe. Expansion behaves the same. Background radiation remains uniform. Galaxies form as observed. The multiverse does not alter everyday cosmology. It sits at the edges of theory, not at the center of evidence. This perspective helps keep the discussion grounded. The multiverse is not required to explain current observations, though it may arise naturally from attempts to explain them. It is one possible extension among several, not an inevitable conclusion. Science progresses by remaining flexible. Ideas are explored, tested where possible, refined or set aside. The multiverse at present belongs to the category of ideas being explored thoughtfully but cautiously. Its status is provisional, its implications debated, and its testability uncertain. By framing the multiverse as a discussion rather than a declaration, cosmologists maintain clarity about what is known and what is speculative. They avoid overstating conclusions while still engaging with the full range of implications that modern theories suggest. In this way, multiverse ideas serve a useful role even if they remain unverified. They push scientists to think carefully about assumptions, about what counts as explanation, and about how far scientific reasoning can extend beyond direct observation. Whether the universe is singular or part of a larger structure remains an open question. For now, the multiverse remains a possibility rather than a finding. It is a conversation about the boundaries of science itself, carried out with caution, curiosity, and an awareness of how easily imagination can outpace evidence. And perhaps that is its most valuable contribution. Not an answer about what lies beyond the observable universe, but a reminder that even our most ambitious theories must remain anchored to what can be tested, while still being open to the vastness of what might exist beyond the reach of light. In everyday experience, space has 3 dimensions: forward and back, left and right, up and down. These directions feel complete, intuitive, and sufficient for navigating the world. Time adds another dimension of change, but space itself seems settled. Yet in modern physics, this familiar picture may not be the whole story. Some of the most ambitious ideas in theoretical physics suggest that space could have more dimensions than the 3 that are immediately apparent. These extra dimensions are not proposed lightly, nor are they introduced for dramatic effect. They arise from attempts to build deeper frameworks that describe the universe in a consistent and unified way. In these ideas, extra dimensions are not large open directions that one could travel through like ordinary space. Instead, they are often imagined as compact, tightly curled, or otherwise inaccessible at everyday scales. They exist everywhere, but remain hidden, influencing physics subtly rather than announcing themselves directly. One way to picture this is to think of a cable viewed from far away. At a distance, it looks like a simple line, one-dimensional. Up close, its structure reveals thickness and curvature. The extra dimension was always there, but it only became visible when examined at the right scale. In a similar way, extra spatial dimensions could exist without being obvious to ordinary observation. These ideas appear in several theoretical approaches, especially those aiming to reconcile gravity with other fundamental interactions. In such frameworks, allowing additional dimensions can simplify mathematical relationships and resolve inconsistencies that arise when trying to describe the universe using a single coherent set of rules. Some proposals go even further, suggesting that the universe we observe may be embedded within a larger structure. In these scenarios, the familiar universe is not all of space, but a region within a higher dimensional environment. Matter and light remain confined to this region, while gravity may interact more broadly. This concept is sometimes described using the language of surfaces or membranes, though these terms are metaphors rather than physical descriptions. The key idea is not that the universe floats in a surrounding space like an object in a room, but that the geometry of reality itself may be richer than everyday perception allows. If such a larger framework exists, it could help explain certain puzzles: why gravity appears weaker than other interactions, why the universe has the structure it does, why certain constants take the values they do. Extra dimensions provide one possible context in which these questions can be explored. Despite their appeal, these ideas remain theoretical. No direct evidence for extra dimensions has been observed. Their existence is inferred only through their potential explanatory power within mathematical models. This is where observation becomes essential. If extra dimensions influence physics, they must leave some trace. Subtle deviations in how gravity behaves, unusual patterns in high-energy experiments, small anomalies in cosmic observations. Scientists have searched for such signatures carefully using a wide range of methods. So far, observations place strong constraints on these ideas. Gravity behaves exactly as expected across a wide range of distances. Particle experiments show no clear signs of additional dimensions affecting outcomes. Cosmological measurements align well with models that do not require extra spatial directions. These constraints do not rule out extra dimensions entirely. They restrict how large they could be and how strongly they could interact with familiar physics. If extra dimensions exist, they must be hidden extremely well, influencing the universe in ways that are subtle and difficult to detect. This is why extra dimensions remain part of theoretical exploration, rather than established science. They are possibilities suggested by mathematics, not conclusions forced by data. Their role is to test the flexibility of physical theories, and to explore what kinds of universes are logically consistent. There is a careful balance here. Theoretical physics allows imagination to roam, but it also demands discipline. Ideas are valued not for how striking they sound, but for how well they connect to reality. Extra dimensions are intriguing precisely because they sit at this boundary between creativity and constraint. From a communication perspective, extra dimensions can easily drift into misunderstanding. They are sometimes portrayed as hidden worlds just beyond reach, waiting to be discovered. In scientific discussion, the tone is far more restrained. These dimensions are not destinations. They are features of equations, inferred structures that may or may not correspond to physical reality. There's also a gentle humour in how invisible these dimensions would have to be. If they exist, they have done an excellent job of avoiding detection. They influence nothing obvious, disturb nothing familiar, and leave only the faintest fingerprints, if any at all. The reason scientists continue to study these ideas is not because evidence demands them, but because they offer potential coherence. They provide frameworks in which disparate pieces of physics might fit together more naturally. Whether nature actually uses these frameworks remains an open question. Importantly, extra dimensions do not change what is known about the observable universe. Galaxies form the same way. Expansion behaves as measured. Background radiation remains uniform. These ideas sit beneath observable phenomena, not above them. They also highlight a broader point about science at the larger scales. Understanding the universe sometimes requires exploring possibilities that extend beyond current evidence. Doing so carefully helps clarify which assumptions are essential and which are optional. Extra dimensions serve as a reminder that reality may be more layered than intuition suggests. The universe could possess structure that is not immediately accessible to senses or instruments, or it may not. Science remains open to both possibilities. What keeps these ideas grounded is the continued emphasis on observation. As instruments improve and measurements become more precise, opportunities to test even subtle effects increase. Theoretical ideas must remain responsive to these results, adjusting or fading as evidence accumulates. In this sense, extra dimensions occupy a provisional space. They are neither dismissed nor accepted outright. They are held in careful suspension, examined for usefulness, consistency, and compatibility with what is already known. Whether the universe is part of a larger framework or entirely self-contained remains uncertain. Extra dimensions offer one possible lens through which to consider that question. For now, they remain an example of how far scientific curiosity can reach, even while remaining anchored to evidence. The universe does not promise to be simple. It does not guarantee that all of its structure fits neatly into everyday intuition. Extra dimensions, if they exist, would be one more way in which reality quietly exceeds expectation, remaining present yet unseen, influencing the whole while revealing very little. Until observation demands them, they remain ideas, thoughtful, constrained, and carefully explored. Not answers, but possibilities. And in science, that distinction matters deeply. Every measurement ever made of the universe carries a quiet reminder with it. There is always a limit. No instrument sees perfectly, no observation captures everything. Even the most precise data arrives wrapped in uncertainty, shaped by the tools used to collect it and the conditions under which it was gathered. Instrument sensitivity is the first and most obvious constraint. Telescopes, detectors, and sensors all have thresholds. Below a certain level, signals blend into noise. Light becomes too faint. Differences become too subtle to distinguish reliably. This is not a flaw in design so much as a consequence of physics. Detecting something requires interaction, and interaction has limits. As instruments improve, these limits shift. Fainter galaxies become visible. Smaller variations can be measured. Yet each improvement reveals a new boundary. There is always a point where increasing sensitivity yields diminishing returns, where background noise overwhelms signal, or where the universe itself provides fewer photons to work with. Some limits are technological, but others are fundamental. Even a perfect instrument cannot escape the constraints imposed by the universe's structure. One of the most important of these constraints is known as cosmic variance. This term refers to the fact that there is only one observable universe to study, and only one large-scale realization of cosmic structure available to us. Cosmic variance arises because observations sample a finite region. When measuring large-scale properties, such as the distribution of galaxies or background radiation patterns, scientists cannot average over multiple universes. They must work with a single cosmic arrangement accessible from this location. At the largest scales, statistical uncertainty remains no matter how good the instruments become. This means that some measurements cannot be refined indefinitely. Even with perfect detectors, there would still be uncertainty simply because there is only one sky to observe. Some features could look slightly different if viewed from another region of the universe, but that comparison is impossible. Cosmic variance places a natural flaw on precision. These limits shape how data is interpreted. Measurements do not speak for themselves. They must be placed within models that describe how the universe behaves. Models provide context, allowing scientists to connect individual observations into a coherent picture. They describe relationships, evolution, and underlying structure. There is a delicate boundary here. Data constrains models, but models also guide how data is interpreted. Where data is abundant and precise, models are tightly tested. Where data becomes sparse or uncertain, models play a larger role. This is not a weakness. It is how science operates at the edge of what can be observed. Understanding where data ends and models begin is essential. Models are not guesses. They are carefully constructed frameworks built from known physics, mathematical consistency, and observational support. Yet they are still representations, not reality itself. They simplify, idealize, and extrapolate. As observations push closer to fundamental limits, reliance on models increases. This is especially true when studying the early universe, distant regions, or phenomena that cannot be observed directly. In these cases, models allow scientists to explore possibilities while remaining anchored to evidence. Managing uncertainty in this process is not left to individuals alone. It is a collective effort shaped by institutions, collaboration, and review. Large scientific organizations coordinate observations, set standards, and encourage transparency. Data is shared, methods are scrutinized, and results are compared across independent teams. Peer review plays a central role here. Before results are accepted, they are examined by other experts. Assumptions are questioned, methods are challenged, alternative interpretations are explored. This process does not eliminate uncertainty, but it helps ensure that conclusions are proportional to the evidence supporting them. Institutions also provide continuity. Large surveys and long-term missions span decades. They outlast individual careers. This continuity allows measurements to be repeated, refined, and reinterpreted as techniques improve. It also helps prevent overreaction to single results that may later be revised. There is a quiet discipline to this approach. Scientists are trained to express confidence carefully. Results are reported with uncertainties attached. Claims are bounded. Language is chosen to reflect degrees of certainty rather than absolute statements. This restraint is not a lack of ambition. It is a recognition of limits. At times, this careful language can feel unsatisfying. It lacks the drama of definitive answers. Yet it is precisely this caution that makes scientific knowledge durable. Conclusions that survive repeated testing, critique, and refinement tend to last. There's also a hint of levity embedded in how cosmologists discuss uncertainty. The universe, it seems, enjoys keeping a few details just out of reach. Measurements improve, error bars shrink, and yet new questions appear. Each answer opens another layer of uncertainty, not because progress failed, but because understanding deepened. Limits of measurement do not halt discovery, they shape it. Knowing where precision fails helps scientists focus efforts where improvement is possible and recognize where speculation must remain provisional. Limits guide curiosity rather than extinguish it. These constraints also remind us that knowledge is contextual. What is measurable today may not have been measurable in the past. What seems unreachable now may become accessible later. Conversely, some information may fade from view as the universe evolves. Measurement is tied to time as well as technology. The role of institutions becomes especially important in preserving knowledge across these changes. Data archives, published analyses, and theoretical frameworks allow future researchers to build on what has already been learned, even if direct observation becomes more difficult. In this way, science becomes a cumulative endeavour rather than a race for final answers. Each generation extends the boundary slightly, clarifies uncertainties, and hands the work forward. The limits remain, but understanding grows within them. There's a deeper lesson here. The universe does not offer complete access. It does not guarantee perfect knowledge. It provides clues, patterns, and signals, and it allows those signals to be studied within constraints. Science adapts to these conditions, learning to work with partial information. The limits of measurement and knowledge are not failures of curiosity. They are features of reality. They define how questions can be asked and how answers must be framed. They encourage humility without discouraging exploration. In cosmology especially, these limits are woven into the subject itself. Horizons restrict observation. Expansion stretches signals. Cosmic variance caps precision. Models extend understanding beyond data, but never replace it. Recognizing these boundaries helps prevent overconfidence. It keeps claims proportional. It maintains trust in the scientific process, and it preserves room for wonder, not because everything is unknown, but because what is known is framed honestly. At the edge of observation, certainty softens into probability. Measurements blur into ranges. Models suggest rather than declare. This is not a weakness of science. It is its strength. Science does not pretend to see everything. It maps what it can, marks where vision fades, and continues forward with care. In the vastness of the universe, knowledge advances not by erasing limits, but by understanding them. And within those limits, remarkably, the universe has already revealed far more than intuition ever promised. Questions about what lies beyond the observable universe have a peculiar power. They do not promise clear answers, yet they continue to be asked across cultures, centuries, and scientific revolutions. This persistence is not a flaw in understanding. It is a feature of how understanding grows. Asking about what lies beyond immediately stretches perspective. It forces a shift away from familiar scales and comfortable assumptions. Instead of focusing on objects that can be seen, measured, and catalogued, the question invites reflection on limits themselves. Where does observation stop? Why does it stop there? And what does that stopping point say about the universe and about knowledge? In science, progress is often associated with answers, measurements refined, theories confirmed, predictions matched to observation. Yet some of the most important advances begin not with answers, but with carefully framed questions. The question of what lies beyond the observable universe is one of these. It reshapes how scientists think about space, time, causality, and evidence. This question also clarifies an essential distinction. There is a difference between what is unknown and what is unknowable. The unknown refers to things not yet measured, not yet understood, but potentially accessible. The unknowable refers to things that lie beyond the reach of observation in principle, not just in practice. Recognizing this difference is crucial for scientific humility. Humility in science is not about lowering expectations or avoiding ambition. It is about aligning claims with evidence. It is about acknowledging where inference replaces observation and where models extend beyond data. The question of what lies beyond the observable universe brings this alignment into sharp focus. Science does not retreat from such questions. It approaches them carefully. It builds models consistent with known laws. It explores implications while clearly labeling assumptions. It resists the temptation to declare certainty where none can be justified. This restraint is not weakness, it is discipline. There is also an important cultural role played by this question. In the absence of careful explanation, unanswered questions can become fertile ground for misinformation. When limits are not clearly explained, speculation can rush in to fill the gap. Walls, edges, hidden realms, and dramatic boundaries can take the place of quieter, more accurate descriptions. Distinguishing between mystery and misinformation matters. Mystery arises naturally when evidence runs out. It invites curiosity without demanding belief. Misinformation, by contrast, presents imagined answers as fact. It replaces uncertainty with confidence that has no foundation. Science protects mystery by being honest about limits. It says this cannot be tested directly. This must be inferred cautiously. This remains open. By doing so, it prevents mystery from being misused. The unknown remains a space for inquiry rather than assertion. The question of what lies beyond also helps explain why scientific language can sound careful, even understated. Words like horizon, limit, and inference may seem less dramatic than edge or boundary, but they carry more precision. They describe processes rather than objects. They reflect how knowledge is actually obtained. There is also a restrained humour in how often science must clarify that not knowing something does not mean imagining anything. The universe does not fill its unseen regions with arbitrary structures just to satisfy curiosity. It follows its laws whether observed or not. What science can say about those regions depends on how those laws behave where observation is possible. Unanswered questions also play a practical role in guiding research. Knowing where understanding breaks down helps focus effort. It clarifies which measurements matter most. It highlights which assumptions are most influential. It shows where new ideas might be needed and where existing frameworks are sufficient. In cosmology, this is especially important. The subject deals with scales and conditions that cannot be reproduced or manipulated. Observation is passive. The universe offers signals, and scientists must interpret them carefully. Asking about what lies beyond observation sharpens awareness of this passive relationship. There is also a philosophical value in questions that resist final answers. They remind us that knowledge is provisional, that understanding evolves, that even well-supported theories are open to refinement. This openness is not a sign of fragility. It is the reason science remains resilient. Future discoveries may alter how far observation can reach or how inference is applied. New techniques may extract information from signals currently considered inaccessible, or they may confirm that certain limits are permanent. Either outcome deepens understanding. Importantly, the value of the question does not depend on receiving a definitive answer. The process of asking, refining, and contextualizing the question already shapes how the universe is understood. It influences how models are built. It informs how results are communicated. It keeps curiosity aligned with evidence. There is also a human dimension to this persistence. Questions about beyond resonate because they mirror everyday experience. Standing at the edge of a shoreline, reaching the horizon while travelling, turning a page and finding more beyond it. These experiences train the mind to expect continuation. Science respects that intuition while also correcting it. It shows that some continuations are real, while others are conceptual. It teaches that beyond does not always mean adjacent. Sometimes it means inaccessible. Sometimes it means untestable. Sometimes it means simply unknown for now. By making these distinctions clear, science preserves trust. It avoids overpromising. It resists filling silence with certainty. It invites listeners and readers into a shared understanding of how knowledge works. There is also reassurance in recognizing limits. If the universe had to be fully knowable to be meaningful, it would be a very small place. The fact that it exceeds complete comprehension does not diminish it. It enriches it. Unanswered questions create space for imagination without demanding belief. They allow wonder to coexist with rigor. They encourage curiosity that is informed rather than credulous. In this balance, science finds its tone. Asking why the question still matters also highlights a deeper truth. Science is not only about describing the universe, it is about describing the relationship between the universe and those who observe it. That relationship includes limits, horizons, and boundaries of access. Understanding where those boundaries lie helps prevent confusion. It helps distinguish speculation from explanation. It helps maintain clarity about what is known and what remains open. In a universe without obvious edges, the question of beyond becomes less about geography and more about epistemology. It is not asking where space ends, but where knowing ends. That shift transforms the question from one of location to one of understanding. And that is why the question still matters. It matters because it teaches restraint, because it sharpens reasoning, because it guards against false certainty, because it keeps curiosity honest. The universe does not owe answers to every question. Yet by asking carefully, science has uncovered a remarkable amount about a reality that stretches far beyond everyday experience. It has learned how space expands, how light travels, how horizons form, and why some regions remain forever silent. What lies beyond the observable universe may remain out of reach, but asking about it has already revealed something important. It has shown how knowledge is shaped by physics, how humility strengthens understanding, and how unanswered questions can guide inquiry without misleading it. In that sense, the value of the question is not measured by what it reveals about the unseen, but by what it clarifies about the seen. It reminds us that science is not a catalogue of final answers, but a method for exploring reality responsibly. The universe continues, vast and indifferent to curiosity. Science continues alongside it, patient and careful, mapping what can be known and marking where vision fades. And within that fading, the question remains, not as a demand for answers, but as an invitation to understand the limits that make understanding possible at all. The question that opened this journey was a simple one on the surface. What lies beyond the edge of the universe? It is a question that feels spatial, almost geographical, as if the universe might end the way a road ends or a map runs out of paper. Yet after moving slowly through what science has learned, that question begins to change its shape. The universe, as far as observation can tell, does not appear to end in the usual sense. There is no final wall, no outer surface, no place where space abruptly stops. What appears instead are horizons, quiet boundaries defined not by matter, but by time, motion, and the finite speed at which information travels. These horizons do not enclose the universe, they describe the limits of connection. When light takes time to travel and when space itself expands, distance becomes more than a measure of separation. It becomes a measure of access. Some regions are close enough in both space and time for signals to arrive. Others are too far, carried away by expansion faster than light can bridge the gap. The universe continues beyond those regions, but observation does not. This distinction matters. It replaces the idea of an edge with the idea of a reach. It shifts attention away from where the universe might stop and toward how knowing works within it. The universe does not hide itself behind barriers. It simply grows in ways that place parts of itself beyond communication. In that sense, the edge of the universe is not a place, it is a condition. It depends on when you exist, where you are located, and how space has evolved up to that moment. The observable universe is not a container holding everything that exists. It is a moving window shaped by cosmic history. There is something quietly reassuring in this picture. The universe does not confront us with an abrupt ending. It fades gradually into distance and time. Light stretches, signals weaken, knowledge softens into inference. The boundary between what can be known and what must be reasoned about is gentle, not sharp. Science has learned to live comfortably in this space. It does not demand certainty where evidence cannot reach. It builds models carefully, tests them where possible, and marks clearly where assumptions begin. It distinguishes between what is observed, what is inferred, and what remains unknown. This careful approach preserves mystery without surrendering rigour. The unknown is not filled with imagined structures or dramatic claims. It is left open, shaped by what is known and constrained by what can be tested. Quiet uncertainty becomes a feature of understanding rather than a failure of it. There's also a calm honesty in accepting limits. Not everything that exists can be observed. Not every question can be answered directly. Some regions of the universe will never send a signal here. Some information will never arrive, no matter how advanced instruments become. These are not technological shortcomings. They are consequences of how the universe behaves. Yet within these limits, the amount that has been learned is extraordinary. Light from billions of years ago has been measured. Patterns from the early universe have been mapped. Expansion has been traced across cosmic history. Horizons have been identified and understood. The universe has proven generous with information, even as it remains vast beyond reach. The question of what lies beyond the observable universe does not resolve into a single answer. Instead, it resolves into a deeper appreciation of how knowledge works at the larger scales. It teaches that reality is larger than experience, and that understanding does not require complete access. There is no final reveal waiting just beyond the horizon, no hidden realm poised for discovery the moment a boundary is crossed. What lies beyond is likely more universe, continuing according to the same physical laws, unfolding quietly and without regard for observation. Or it may hold surprises not yet imagined. Science remains open to both possibilities, while claiming neither. This openness is not indecision, it is precision. It reflects a commitment to matching claims to evidence, and allowing uncertainty where uncertainty is warranted. It is a way of honouring both curiosity and restraint. For the listener, this leaves not a sense of frustration, but a sense of scale. The universe does not end because our questions do. It extends far beyond them, indifferent yet consistent, governed by rules that allow much to be known and some things to remain silent. There is comfort in that silence. It suggests that mystery does not demand resolution to be meaningful. Some questions enrich understanding simply by being asked carefully. They invite reflection rather than answers. They widen perspective rather than close it. As this journey draws to a close, the central question remains, but it feels gentler now, not sharper, not more urgent, but more spacious. What lies beyond the edge of the universe becomes less about reaching a destination, and more about understanding the limits of reach itself. The universe may not have an edge in the way intuition expects. What it has instead are horizons, shaped by expansion and time, boundaries of connection rather than boundaries of existence, places where knowing gives way to inference and inference gives way to quiet acceptance, and within those horizons there is still so much to explore, patterns to measure, light to collect, models to refine. The unknown does not diminish what is known, it frames it. So the universe continues, Vast, dynamic, and largely indifferent to being observed, science continues alongside it, patient and careful, mapping what can be known and marking where vision fades. And perhaps that is enough. Not a final answer, but a calm understanding. Not a resolution, but an openness. A recognition that the universe is larger than any single viewpoint, and that within its quiet limits, curiosity can rest without needing to be satisfied. For now the universe stretches outward, silently, beyond observation. And that silence is not emptiness. It is simply the farthest reach of light, and the gentle boundary where knowledge pauses, not in defeat, but in balance.